This week, for the most part, we're going to be looking at the graphs of exponential functions with the transformations. The three particular transformations that we're going to be checking out here are the a value, the h value, and the k value. You do see the letter b, but that's going to be different than the b values you had used in some other functions. And that b value, which implied all the horizontal compressing and stretching, that is not going to be part of the stuff that we're going to look at here. So you do have the a value, which is that vertical stretching and compressing. You do have the h value, which is going to be the horizontal shifting. You also have the k value, which is going to be the vertical shifting. And recall that you do see here a minus h because whatever you actually see in the function, you're going to interpret that the opposite as you shift left and right. So for example number one, we're going to be graphing this function. You're going to notice that it chose the same base, which is 2, that we used in the previous set of notes. The reason I did that is because you're going to be a little bit more familiar with what that graph looks like on its own, or you can even go and get those notes out and you can do a comparison. But what I'm going to do is recap just the coordinates that we used to graph that. Remember that the most important coordinates that we're going to be using is when your input is a 0 and a 1. Because when you raise something to the 0 power, you always get back 1. So you're guaranteed that coordinate. In addition, when you raise to the first power, you're going to get that base as the response. So those would have been 2 points that I could plot, one here and one here, if it didn't have any transformations. So the way that I'm going to deal with this is I'm going to take care of the transformation portions of this at the very beginning. Okay, so the parent function had a horizontal asymptote at the x-axis. But what we're going to end up doing because of that minus 5 is shifting the whole graph down 5 units. So that's going to actually put your horizontal asymptote at -5. So you should take that in for a moment here and say, that's pretty darn convenient. Whatever that constant is at the end, that is going to be your horizontal asymptote. And it will be consistent throughout as you do problems. Okay, in addition to that, what I'm going to do is think about this shifting. The whole graph is going to be moving to the right. Right? There's a negative here, so we're actually going in the positive direction. You're going to be moving to the right 4 units. So I drew a line right here. And the way that I'm going to now interpret this stuff, I'm going to think of this as being that horizontal asymptote at the x-axis. So this is my x-axis now, and this is going to be my y-axis. It isn't because this is where the axes actually are, but I'm going to pretend that that's where they are. And when I do that, I can start plotting this function without the transformations as if that was my origin. So if I want to plot the point 0, 1, which is no longer here, it's actually right there. So my origin, and then just move up 1 point. And then this point is going to be over 1 unit and up 2. And I can continue to build the table that goes with 2 to the x power and just plot all the points around from there. So if you plugged in a 2, then 2 squared would give you 4. You plug in a 3 and you get an 8, and I can start to plot those points. And everything's just measured off here, so don't pay attention to the other numbers that we have. The opposite direction, everything's going to get cut in half because we're dividing down. They're also reciprocals, whatever you see here, so that'll be 1/2. This is going to be 1/4 and then an 1/8. And to the best of your ability, you're going to attempt to draw that curve. And actually, that one turned out pretty good for me here. All right, if you want, you can do a test value. Okay, so let me choose something that, just a random point. So suppose I'm going to take that point, which is at 6, -1. I want to test that out in the original function. So what we're hoping is that the output is going to be -1 when the input is 6. So let's check it out. First, you're going to go ahead and subtract those exponents, which is going to give you a 2. So we got 2 to the second power minus 5. 2 to the second power is 4, and 4 minus 5 is, in fact, -1. So our equation, at least on that 1 point, but I can tell you it will for the rest, is working out. All right, domain. You know, nothing's really changing with just some shifting over here, so you're going to get all real numbers. You go -infinity to infinity. The range. Son, I'm trying to record a video on math. Yeah, distance learning. My son just showed up like a minute ago, and Now he wants to ask questions about my lighting. All right, where was I? Range. You're still going to be above that asymptote, so we're going to have an open interval at -5, and it's going to go up to infinity. So there's a lot of redundancy in what you're going to see for the domains and ranges.
It's like glass.
Yeah.
Then those two, each of them.
Okay. Okay, examples 2 and 3, what we're going to look at is bringing in a little bit more at the transformations. In number 2, the particular thing here is the A value and how we just address that. I'm still going to start with the shifting portions here. Since I have the -2 as that constant, it's going to bring that horizontal asymptote down to -2. Because I don't have anything after that x up there in the exponent, then we're not going to be shifting left or right. So I'm going to highlight the y axis. I would suggest that if you're going to use this method that you still highlight it even if it is the y-axis, because it sets kind of a tone for where the origin's at, and it just seems to make sense, so I'll do it anyway. Okay, with that out of the way, we just have to address the fact that we have a 4 as the base, and then we also have the 1/2 that's sitting out there in the front. So now I'm going to go over and start to think about a table if I didn't have that 1/2 and it's just the 4. So your points you always want to use are 0 and 1. That's going to give you a 1, and then I'll show you your base, which is a 4. Now, if you raise it to the second power, that's going to be 4 squared, which is 16, which is a fairly large number, but we'll see how this works out. If you raise it to the third power, you can get all the way to 64. Okay, on the other end, if you start using negatives, you're just going to get the reciprocals of these numbers. So you get almost row negative. You actually get 1/4, and then you get 1/16, and so on. Okay, so now instead of going from this point and saying there's a dot here, right, like the 0, 1, and just going up to that, and then doing maybe over 1 and up 4, which you would do if there was no 1/2, all we're going to do is change the output portion of that by taking 1/2. So we are compressing it to 1/2 when we do this. So instead of going up 1 at 0, you're actually just going to go up half of that. So you get a dot here. Then at the next spot, so instead of going over 1 and up 4, you're actually just going to go over 1 and up 2, half of whatever that number is. So that'll give you a point there. Then this, you actually can see, you might be able to graph it. When we go 2 units over, we're going to be going up 8 units instead of the 16. So I got 2, 4, 6, and 8. Then everything, of course, around that line is just going to be flipped. So 1/4, you just sort of guess, and to be honest, don't plot any more points out from there. When you do make these, there's a chance that you're not going to get that many coordinates out of it. But if we can maybe see that one approximated correctly, then a couple like whole value ones, then that'll be fine. So your domain is going to be all real numbers. Your range is going to be bounded at the -2, and it's going to continue to go up forever. So we're not really seeing too much stuff that's different there. Example 3, the change is mostly going to be that negative. These two pieces we've already done a couple of times, so I think you'll be able to follow that. The horizontal asymptote moves up 3 units for the +3. Because we have a +4, we're going to be moving everything to the left 4 units. So I drew a line here at -4. So all that's out of the way. I actually start to look at this as 3 to a power. The negative is something that's happening afterwards. In fact, even, this is kind of confusing, but even if it said this without the parentheses, the negative is something that happens at the end. It's only going to be the 3 that's raised to that power. If you were to put the -3 in parentheses and make it negative and you're raising that to the powers, that's what it would look like. But we don't do that. And if you go back to the first video, I started to mention that you can't take the negative and keep raising it to powers because of the changes that you're going to have between positives and negatives. And even if you use like a fraction, you can get imaginary numbers. So that negative, just be advised, it's always like a last part to it. Okay, so let's see, our basic coordinates, you're going to get 1 and 3 from those. All right, in addition, we do a couple extras, like if you did a 2, then that'll give you a 9. -1 is going to give you -1, or it's not negative, it's going to give you 1/3. So I keep making that little mistake for just a moment where I'm about to write a negative, but it's actually a reciprocal. You don't end up creating any negatives out of these. That's kind of interesting, right? That this stuff is not negative like ever when you build a table. It will become negative though because of this in just a moment. Okay, so treating that like it's my origin and then wanting to graph from there, this would indicate that I would go down 1 unit here, and then over to the right I would go down 3 units. Oh, I'm already graphing because I know the right direction. This would actually indicate that you go up 1 and then you go over 1 and up 3. But the negative, that's that a value, is going to change everything. So now you're going to think -1, -3, -9, -1/3. So instead of going up 1, you're going to go down 1. Sorry, I got a little bit ahead of myself there, but at least I was actually doing it correctly. All right, so we'll go over 1 and then we'll go down 3. If you can fit that 9, yep, I give myself enough space here. I can go down -9, and then here, you just kind of ballpark it. Not too worried about it. It does help to put the dot, help you try and connect these things. But I'll be honest, it's hard to hit those points perfectly. I always have trouble with it. Anyhow, that's the graph, and I didn't do it for number 2, and I don't know if I'll do it for number 3 here either, but take a coordinate that's just out there. Like that one seems pretty cool that we have some point here that's at -3, 0. That seems interesting. And take those numbers, put the 0 in, no, put the -3 in for the x, and work all this out and see if it actually turns out to be 0. And it's kind of neat to see that it does. All right, your domain. Look, no surprise, it's all real numbers, but your range has finally done something different. It's not on top, it's on the bottom part. So you're gonna write it like this. It's -infinity. Yeah, let's try and make that look a little bit better. It's gonna be -infinity up to 3, like that. Notice the switch because you are coming from the bottom up to 3.